All right, welcome to today's Explainer. Listen, I'm stepping in today as your elite Cambridge exam flight director. We are treating Cambridge AS and A-level mathematics topic 6.4, that's sampling and estimation, specifically confidence intervals for population proportion, like a high-stakes multi-billion-dollar flight system that requires absolutely perfect execution. You are the pilot here. The exam paper, that's your central console screen, and your ultimate objective is to clear orbit with maximum marks. Today, we're going to break down the exact telemetry you need to succeed, all the way from calculating your standard errors to interpreting those tricky z-values. So strap in, run your preliminary system checks, and let's initiate our pre-launch sequence. Okay, let's dive right into this because this is huge. The principal examiners themselves, the supreme commanders setting our flight parameters, have identified this specific topic as a critical failure point across the board. They've literally reported that confidence intervals for population proportion is one of the most misunderstood areas in the entire mathematics syllabus. Wow, that is a massive, blinking red flag on our radar. If we don't lock in our exact coordinates today and fully understand the underlying mechanics of what we're actually calculating, we risk a catastrophic loss of method marks. But hey, we are going to fix that right now. I'm going to show you exactly what these examiners are scanning for when they look at your paper. So here is our mission flight plan for today. First, pre-flight core concepts to fire up our foundational engines. Second, telemetry for extracting your data. Third, mapping our trajectory with technical methodology. Fourth, evading turbulence by looking at examiner warnings. And fifth, our touchdown sequence, the evaluation. Initiating Section 1, Pre-Flight Core Concepts. Let's get our systems online. Right, before we can even think about leaving orbit, we absolutely have to establish our theoretical architecture. The assessment objectives for this module are explicitly targeting distinct cognitive domains, prioritizing deep analytical understanding over just superficial breadth. Here's the thing. The biggest hurdle you're going to face isn't just knowing the math itself. It's being able to apply a connected, conceptual understanding to completely unfamiliar flight conditions. To survive these unfamiliar contexts, your theoretical architecture must rest on incredibly precise definitions. It's not just about memorizing the confidence interval formula. Anyone can do that, right? It's about truly understanding the causal relationship between your sample size n, your variance, and the margin of error. When the examiners dress up the scenario in some wild, unpracticed context you have never seen before, you have to rely on these conceptual instruments. You have to trust that the fundamental mechanics of population proportions remain completely constant, no matter how the question is framed. Moving on to Section 2, Telemetry, Extracting Exam Data. Let's look at how we process incoming signals. Okay, so in the exam, every single word, every number in that question block is a command keyword, acting as a crucial system parameter. I want you to imagine a 60-second visual countdown clock ticking down on your console right now. In this exam's simulation, you have to rapidly extract variables from dense text blocks and really highly complex tables. You need to identify your sample size n, your observed proportion p hat, and pull the exact z-value for your required confidence level. It has to be fast, and it has to be accurate. Your extraction strategy must be completely systematic here. Identify the given information, lock onto the specific context, and immediately map out any cross-topic connections to secure those deeper analytical marks. Honestly, if you misread the signal here, your calculation might be perfectly executed later on, but you'll completely miss the landing zone because you started with the wrong coordinates. Section 3, Trajectory, Technical Methodology. Time to lock in our flight path. With our data telemetry successfully locked, we need to map out our answer framework on our console overlay to execute what I call the method mark strategy. This is a standardized 5-step procedural framework designed to guarantee you pick up every single method mark along your flight path. Step 1, deconstruct the question completely. Step 2, extract the relevant data, meticulously tracking your variables. Step 3, select your analytical framework. Like, ask yourself, are you utilizing the normal approximation for the binomial distribution here? Step 4, execute your analysis with absolute crystal clarity. Deploy your standard error calculation, the square root of p times 1 minus p over n, and ensure your upper and lower bounds are stated distinctly. And finally, Step 5, present them using the correct terminology. Follow this sequence, and I promise you, this is your stabilized flight path. Let's actively monitor the approach trajectory by comparing two student flight simulations right now. We've got Pilot Alex and Pilot Sam. So, Pilot Alex attempts to solve the problem by drastically overcomplicating the data calculations. Alex is burning way too much vital exam fuel trying to derive formulas from scratch rather than just applying the standard framework. It's a massive time drain. On the other hand, Pilot Sam ignores the structural boundary constraints entirely. Sam does the math in his head, skips the entire working out phase, and completely ignores the formatting requirements. Both of these trajectories, they are failing. Systemic breakdown imminent. Now, Before we fire the secondary boosters to correct these errors and secure maximum marks, you need to optimize your own flight path. Subscribe to AC Exams at the handle @AceTheExams right now, and turn on all notifications so you don't miss any critical updates. All right, resuming simulation. Let's override the console right now and inject the PEAL protocol to save their trajectory. PEL, point, evidence, evaluation, and link. You state your point, you back it up with mathematical evidence from your calculated confidence interval, you evaluate what that actually means for the population, and then you link it right back to the specific context of the question. That, my friends, is exactly how you stabilize a turbulent answer.
Section 4. Turbulence. Examiner warnings. Time to navigate the rough air.
Look, every flight hits rough air, and we need to prepare for it. Here are the top systemic failures reported across the entire Cambridge network, straight from the examiners. First, candidates are simply forgetting to include proper mathematical format. They are dropping incredibly easy marks just because they didn't write out the confidence interval brackets correctly. Madness. Second, they are failing to check their precision limits and overall presentation. Third, and this is a big one, they are writing generic robotic textbook answers that are entirely detached from the specific context. Listen to me. If the question is about the proportion of defective microchips, your answer better explicitly mention defective microchips, not just drop an abstract P and move on. And finally, examiners are seeing candidates consistently confusing key terminology, catastrophically mixing up sample proportions with population proportions. Don't be that candidate. Okay, I want to initiate our live, interactive viewer radar challenge, debris detection. I am actively tracking your radar right now. Whenever you finish a long-form extended response, you must run a quick debris detection scan. You are literally looking for the exact sentence where a sample answer falls below compliance standards. Ask yourself, did you drop the specific context? Did you use a variable like p hat or z without explicitly defining it first? The principal examiner reports literally demand, that you always define your terms before applying them to the extended response. If you spot undefined terms in your own writing, that is debris. Clear it out, define the terminology, and re-engage your thrusters.
Section 5. Touchdown. Evaluation. Final approach sequence initiated.
We are on final approach, everyone. This is where we transition from purely mechanical calculation into the higher order critical analysis phase. Top scoring candidates, they don't just calculate a number and walk away. They use a strict deconstruct, solve, evaluate protocol. First, solve the problem systematically, tracking every single mathematical step. Second, and this is absolutely crucial, check your answer for reasonableness. Seriously, if you calculate a confidence interval for a proportion and your upper bound is above 100% or 1.0, your system has critically failed. Proportions cannot exceed 1. You must recognize that error immediately. Third, demonstrate your evaluative thinking by questioning assumptions and making justified recommendations backed entirely by the concrete statistical evidence you just calculated.
To ensure perfect execution under immense exam room pressure, you need a fail-safe. Think of our 5 methodology steps: extract, select, execute, present, evaluate. That gives us the letters E, S, E, P, E. I challenge you right now, jump into the comments and create your own catchy memory hack acronym for ESEPE. Come up with whatever weird, memorable phrase you need to construct to lock down your confidence interval procedures. This mental shortcut is going to act as your emergency backup generator when the exam pressure spikes and you need to quickly recall the exact structural boundaries of your answer. Let's see who comes up with the best one. As we conclude this explainer, I want you to distill everything we covered today into your own personal pre-flight question scan checklist and keep practicing those past paper questions. Make sure you subscribe to Ace the Exams at the handle @AceTheExams, enable that notification bell so you're ready for our next masterclass, and drop a comment below sharing your specific subject and tier along with that acronym we just talked about. But before I sign off, I'm going to leave you with this final critical thought to ponder. A 95% confidence interval does not mean there's a 95% chance that your specific population proportion is inside that specific boundary. Mind-blowing, right? Actually, what it means is that if you repeated this flight simulation infinitely, generating sample after sample, 95% of the intervals you construct will contain the true population proportion. So, ask yourself, are you confident in the interval you just built? Your trajectory is clear, your systems are updated. I'll see you on the next flight.